In this video, we are going to discuss about how to solve the linear regression problem using the least square method, and also how to derive the normal equation, which is the solution of the linear regression problem, and it is a closed form solution. So first, let's define the linear regression problem. So what we have per hand. So we are given the data set. The data set consists of two different types of variables. We have n input variables. Those are denoted by x1, x2 through xn. And we have one output variable, which is y. Now typically this x variables are called predictor variables or input variables, and the y variable is called a response variable. And for linear regression, this response variable is going to be continuous in nature. So again, linear regression is going to be a form of supervised learning problem. So we'll be given this input data set and the output labels, the vector output labels, and we are going to find a linear function that basically maps this input data set x to the output vector y using some linear transformation. Now, in one dimension, this can be viewed as drawing a straight line, finding the best fit line in the xy plane, and in the two dimensions, if we have the input variables, two input variables, we are going to have fit a plane that gives us minimum error, and some of the points are probably going to be above the plane and some of the points are going to be below the plane. And again, our input data set x is going to have, let's say, m rows. We have m data points, and it is going to have n columns corresponding to n input variables, and the labels vector is going to have m elements, and this data set we are going to call training data set, because we are going to train our function or the linear model from this data set. Now again, coming back to our original problem. So basically, we can think of the input dataset x as an m by m matrix, and the output vector as again an m by 1 vector. So in case of least squares, what's our goal? So what the model is going to learn from the data. So we are going to learn a function from the data, and we are going to fit a model using the function f that maps from x to y, and it is going to give us the least error on the training data set. And this function, being a linear function, can be expressed as x times w. where X is our input matrix, which is an m by n matrix, and W is the parameter vector that we are going to learn. This is an n by 1 vector, and we are going to learn from the training data through our least square method. Now, the least square method is going to guarantee that the function that we are learning, the error or deviation from the actual output variable from the function output should be minimal, and we are going to minimize. So this can be formulated as an unconstrained optimization problem, where we want to on the parameter W, and the solution is going to be what is known as the normal equation, and it is from the last page. Now let's derive the normal equation, which is the solution using the least square method. So again, restating the least square problem as minimizing an unconstrained minimization problem, where we want to minimize W and we want to minimize the L2 norm, the square of L2 norm basically, of xW minus y. This is going to be again a vector. And basically this square of L2 norm can be written as an inner product of this form. And if we expand this inner product, we are going to get this. Again, taking a product, we are going to get these 4 items. The first one being W transpose X transpose XW. The second one being W transpose X transpose Y. The third one being Y transpose XW. And the fourth one being Y transpose Y. Let's call our error function or the loss function or the cost function to be named as J. We are going to assume that it is a function which is continuous in W and also differentiable in W. So in order to have a local minimum, the derivative should be 0 at the point where the local minimum belongs to. So since we are dealing with matrix and vectors, we need a set of matrix and vector differentiation rules in order to perform this differentiation, and here are the 3 rules that we are going to use. So first rule is del x of ax is going to be A, where A is a matrix and x is a vector. A is an m by n matrix and x is an n by 1 vector. Similarly, we have del x of x transpose A is A transpose, and we have the third rule as del x of x transpose Ax as x transpose multiplied by A plus A transpose. Now we are going to need a fourth identity, which comes from the fact that x transpose x is a symmetric matrix, so that x transpose of the matrix x transpose x is going to be itself. Now let's come back to our original equation, del J del W equals to 0, and using the 3 rules we get W transpose X transpose. So first of all, we are going to differentiate the first term, and we are going to use rule 3, and we are going to we are going to get this expanded term. Then we are going to use the rule 2 for the second term, and for the third term we are going to use rule 1, right? Yeah. Now the fourth term that existed in J, that doesn't involve any term in W, so that gets cancelled away since this is a constant in terms of W when differentiated. Now again, simplifying, what we are getting, we're going to get this W transpose X plus X transpose X minus Y transpose X minus Y transpose X equal to 0. Again, simplifying, we are going to get W transpose X equals to Y transpose X. Now, taking transpose from both sides of the equation, we are going to get W transpose X whole transpose equals to going to be Y transpose X whole transpose. Again, using the matrix transposition rules, we are going to get X transpose X W equals to X transpose Y. Now, multiplying both sides by X transpose X inverse, assuming that X transpose X inverse exists, the solution we get is W equals to X transpose X inverse X transpose Y, and that is enough.